on Canvas yet. I'm going to do that very quickly and then we'll commence with the lecture, okay?
Material assignment now, which is going to be file. So associated with create files, choose file, downloads, extra second transport layer, open.
Hello, welcome to CSC8021. Again, my name is Ian Dixon, and today we're going to be talking about the transport layer. Okay? And very quickly, I put the slides up on Canvas now. Oh, sorry about that, thank you. So hopefully you should be able to download them and walk through them as we go through the slides. And if there's any other technical problems like that, just shoot your hand up. I'll try and fix it before we continue, okay? So, the transport layer. So previously we've talked about the physical layer, we've talked about the network layer, we've talked about, what was the one before that? Blanking, sorry? Data link, there we go, data link layer, thank you. So today we're talking about transport, right? We're going up the OSI stack, so we're just underneath application. And effectively, transport exists as an intermediary between the network layer and the application layer. So the transport layer is responsible for providing a reliable end-to-end connection between two nodes in our network. And sort of like the data link layer, we're going to extract away all of the intermediary nodes in a network. So we're only considering your host and your destination, right? So source, destination, or you know, client, server, whatever terminology you want to use, but the thing that sends the data or needs to get something and the thing that has the thing that you need to get from. So one of the advantages of this is we're abstracting away all of the physical stuff, as I talked about, all the intermediary stuff. So we're just thinking about it for a very high level. And effectively, we're going to take in a network address, also known as an IP address. So that's the like 127.0.0.1 thing that you see sometimes when if you run like ipconfig or something in your terminal, you'll get IP addresses. And then there's also the transport address, which is also called the port. So looking here, the IP address is the address from the network layer, and then the port is going to be the address that gets us through to the application layer. So you can have a single IP address that recognizes a machine within a network, and you can have a whole variety of ports that machine is listening on to try and receive packets of information. So comparing the network layer with the other layers of the OSI stack, it has a lot of the same functionalities as the data link layer. We're sort of extracting away all the intermediary nodes, just sort of start and end, which is good. But while the network layer and the layers underneath are run by communications providers and sort of automated processes with packet forwarding between routers, the transport layer is run by communication between two hosts, right? So the data link layer, we have some sort of physical connection. There might be a bunch of intermediary nodes along that connection. So routers that forward our packets through our network to get to some end goal. But in a transport layer, something happens in the middle. We're not exactly sure, but it will get from point A to point B, right, in between two clients or two hosts. So here's a couple of well-known ports. Right at the top, you do not need to memorize these. That's, unless you specifically want to become sort of a network engineer or a network admin, might be useful. But otherwise, it's not necessary. A couple of the big ones are going to be port 22 for SSH. You've got 80 for HTTP, 443 for HTTPS, which is HTTP over a secure link. But yet again, not necessary. I just wanted to show you an example of what a couple of very commonly used ports are. And within sort of the realm of all of these possible ports, they go from sort of, actually I don't know if there's a zero, but it goes from very, very low numbers all the way up to sort of 9,000, right? And a whole bunch of these ports are what we call reserved ports. So I've listed these ones here. And it's, if you're attempting to build a program that listens on a particular port, and you use one of these reserved ports, you're going to get flooded with a bunch of information you don't necessarily care about, because that port's reserved for some particular process, right? So really, the only reason you need to know these is to avoid them if you're trying to build your own application, or if you want to utilize that service. Otherwise, not necessary to memorize. But here's sort of an example of what you get with kind of we talked earlier about IP and ports. You're going to have the IP, which is this part right here that identifies a particular machine within a network, and then the port right here at the end. So when you run something like ipconfig, it'll be a bunch of numbers, and then a colon, and then a couple of numbers afterwards. Before the colon, that's the IP. After the colon, that's the port. And together, we call this combination of IP and port a socket. So when you're writing code, for the most part, you'll be writing code in the application layer, right? And you'll still need to utilize some of this underlying technology, so you're going to be creating sockets to talk between two machines. So for instance, if you wanted to build a chat client or a file transfer service or something. So the base unit we have within the transport layer is called the Transport Protocol Data Unit. It's just a packet that has some sort of payload, some sort of information that we need to store on the inside, and then we're going to have a header, which is the header of any packet is just the information that describes what happens in that packet. So it might be stuff like the size of the packet, it might be the order in which it occurs in a stream, all sorts of different ways that can be constructed. We'll look at a couple of specific examples of types of packets later, UDP and TCP, but for now, sort of the general structure. And this is a very important concept to sort of understand. We start at the application layer for the most part, sometimes in the transport layer, and we create a packet, so this internal packet, and then it gets passed from the transport layer to the networking layer, where we then, that packet, the original packet, the packet from transport layer, becomes the payload for the next layer, and then we affix a new header. And then that network layer packet gets passed to the data link layer, and the network layer packet becomes the payload for the data link layer. So it's sort of like a Russian nesting doll, if you know what I mean, which is sort of packet within a packet within a packet. And we put all these encapsulations on top of our packets, make it all the way down to the physical layer, send it across to some other machine, where it's then unwrapped until we get back to transport or application layer, where it's then utilized for whatever purpose. It might be congestion control for an application. It might be to just deliver the payload to whatever application you're using. So there might be, video games, for instance. Yeah. So that's sort of what I mean here. It kind of gets encapsulated and then works its way back up. Here we go. So we have sort of three main ways we can do things within the transport layer. We have what's called unicast, which is a one-to-one transmission. So that's sort of the easiest one to think about, right? We have one node we're starting with, right here, and we have a whole selection of nodes at the end. And a unicast is where we pick a specific destination, and we say, I'm going to send information from myself to you. So we establish a link, and we send some sort of information. That's how you do a unicast. A multicast is a one-to-many transition. So you might have two nodes within the network you want to communicate with. Might be, I don't know, I'm trying to think of a good example. Like If you're trying to play music off of 2 speakers within your local intranet in your house, right? And you have a whole bunch of nodes in your house that are communicating on the same sort of network infrastructure, you might want to specifically pick those 2 speakers and send music packets to those 2 machines to then play music, right? Actually, I have a friend of mine, Dale, who's working on a project like that right now. And then broadcast, which is sort of the one-to-all. So it's effectively saying, you know, I exist on the network, I know all of you exist on the network, I'm going to transmit my packet to everyone, regardless of whether or not you want it or not, which can be annoying. So as you begin to work with networks, you might get lots of noise from broadcasts from machines. And that's why, if you want to be a good computer scientist, typically speaking, we discourage doing broadcasts unless it's on a network that you yourself are controlling and designing. If it's a shared network, probably don't want to be broadcasting packets left, right, and center. But an example of a technology that might use this would be like a printer on a network. So if you've ever connected your machine to a Wi-Fi or Ethernet system within a building, and you suddenly get a pop-up that says, oh, this printer can be connected, it's probably broadcasting on that network saying, you know, I exist, please use me. So we're going to talk about the transport protocols. So in order to send a packet on the transport layer, we need to have a agreed upon method of what these packets look like, right? And that's where these transport protocols come into play. So we have 2 main ones. We have the Transport Control Protocol, or TCP, which I think a lot of you have probably heard of before. And just as sort of important, we have the User Datagram Protocol, also called UDP. And UDP is a connectionless protocol. It's also called fire and forget. So if you see connectionless or fire and forget, these sort of terminology, we're probably going to be talking about something like UDP. There is also a connectionless version of TCP, but that's a bit beyond the scope of this. So I'm just going to talk about these 2. And because we're not establishing a connection, we don't have all this connection overhead. We'll talk about what connection is in a few seconds. But because we don't have all of this connection overhead, it's a lot faster than TCP. Because TCP, you have to stop, establish a connection first, and then you can start sending packets. UDP, you just fire, right? Which makes UDP commonly sort of the protocol we use for multicasting and for broadcasting, and TCP tends to be for unicasts. Although you can do multicasting with TCP. It's just a lot slower. And then TCP is our connection-oriented protocol. So we have to establish a connection first, make sure 2 hosts agree upon communication, and then we can start firing packets. And so good examples of sort of where UDP is used versus TCP. So UDP is used in a DNS lookup, so looking up sort of IPs and stuff across multiple subnets on a much larger network than what we locally have. And updating information like that is usually done in something similar to distance vector routing, which we talked about last lecture and yesterday in the session yesterday. Online video gaming, because we can send off a packet, right? And same thing with video streaming. We can send off lots and lots of packets over and over and over again. We don't necessarily care if we lose a few packets, right? We don't have to establish a connection to ensure that those packets get resent. So it's perfectly fine to use something like UDP in these cases, because we just want fast, and it doesn't mind if we lose something. Whereas in TCP, we have to establish a connection. So we're going to, if something goes wrong, TCP has methods to correct itself, which makes it much more useful for things like email, where if I send an email, I expect that email to be received by the person I send it to. I don't necessarily want to fire the email off into the void and for no one to ever read it. So TCP is a good example of that. Back to this slide. So we've got SMTP is an example of something that uses TCP, and same thing for POP3. And then we also have so web pages, right? When I query a web page, I expect that web page to come back up. I want to be able to access it and read it and look at it, right? And if something incorrect happens, I want them to resend me the information for their web page. And same thing for file transfers. So if you SSH into a machine, or if you, FTP, file transfer protocol, I expect the file that I'm sending from my host node to my end node to be received. So TCP is a good use case for that. So what is UDP? What is the User Datagram Protocol? We have an example of, there we go. We have an example of what a UDP packet looks like. So it's usually 32 bits big. We have the source port, so the source port for the machine that we're sending it from, as well as the destination port of the machine we're sending it to. We'll have the length of the packet, because it's 32 bits sort of wide, if that makes sense, but it could be multiple packets long. And then we have our payload, or the data that comes through. And the checksum is optional. That's kind of one of the nice, in massive air quotes, things about UDP, because if you don't provide a checksum, there's no way to verify that that packet is correct, which means you could be reading malformed packets and assuming that they're correct, right? But anyway, so it was originally designed for one request, one response applications, where having to have all that overhead to set up a connection was too much work. And consequently, it's an unreliable protocol because we don't establish a connection, there's no error checking or error correcting. It's not very popular in the 21st century because, yet again, a lot of these guarantees we expect from the internet, to be able to query something and receive something that is correct and in order, UDP does not provide. And some people have facetiously called it sort of an IP packet with an extra header on top of it. We talked about the headers earlier, where we have the payload and the header. That's effectively sort of what UDP is. It's not very fancy. And then lastly, this is sort of important if you ever do work with UDP, there are a lot of systems that by default just reject UDP that aren't being sent to a port that's specifically listening for UDP packets, because it's an excellent way to try and hack somebody, to provide information that's incorrect and gain information about their system, to just broadcast UDP packets on a network and hope that you get a response from the user. So yeah, it might be a good idea to try and limit the UDP packets that come into your system, and consequently a lot of them do just by default. So keep that in mind when you're designing your systems in the future. And then we have the Transmission Control Protocol, or TCP. So it's a lot more robust, right? If we just compare the format between a UDP packet and a TCP packet, we can see there's a lot more stuff happening here. So of course we have a source port, a destination port, let us know where we came from and where we're going to. We have a sequence number, which we'll talk about in a little bit, but it lets you know which packet in a stream that you're talking about. We have a bunch of reserved information, flags that sort of let the system know more information specifically about that packet. If you're interested in that, I do some research into flags. There's a whole bunch of them. The window size, which we'll get into when we talk about sliding windows. Checksum to verify that the packet is correct. Just a bunch of options you can provide. And then this would be the payload of the packet, so the actual information that's being sent. So all of this stuff we consider the header, and then this stuff here, the data is the payload. So TCP was designed to be a robust protocol that exists on an unreliable network, right? Because the internet, as fantastic as it is, its best effort, we have no guarantee that the packet we've sent will be received. So TCP is the sort of network layer thing that allows us, that's fine. Anyway, I'll try to ignore that. So TCP is the transport layer thing that allows us to fix the unreliableness of the internet. Okay? And you have to establish an end-to-end connection between two hosts. So two hosts have to agree to set up communication before you can start sending packets. And the way that we do that is called the three-way handshake, which we'll talk about in the next slide. And then as you're sending packets in a network, right, last lecture that I was here for back on Monday, we talked about the concept of congestion, where too many packets hit some sort of node, and we can't handle those packets, and packets get thrown away, right, because we can't handle it. TCP implements something called a sliding window protocol to try and accommodate that a little bit better. But then we'll talk a little bit more about something called TCP slow start, and then combination with that we have threshold, that we kind of mix them together. We'll see what we're talking about in a sec. Nice this way. There we go. Three-way handshake. So if anybody here has heard SYN or SYNAC before, that's what we're referring to here. So In a TCP three-way handshake, we want to establish a connection which prevents duplications and allows the sender and the receiver to reject packets that aren't established in a connection, okay? And this is how we do that. So we have what's called a SYN packet, or synchronization packet. So it allows you to sync between two nodes. And back from the, this one right here. Back from the TCP protocol, we have a sequence number right here. And what we do is we generate a sequence number for this particular connection. It might be 0, right, very unlikely. It's probably going to be some random number that's relatively large. And we're going to send that synchronization request along with the sequence number from the sender to the receiver. So that's step 1, it's called SYN. And then we have step 2, which is called SYNAC. So we're going to send back a synchronization request with the receiver's sequence number, call that Y, along with an acknowledgement of the synchronization request from the sender. And the way that we acknowledge that synchronization request is we take the sequence number X and we go ahead and we just add 1 to it and we send that back as an acknowledgement packet. So that's a SYNAC, it's from the receiver back to the sender. And now the sender sent our synchronization to the receiver. The receiver has received that and acknowledged it and sent back its own synchronization request. So the last thing we need to do is send back an ACK, or an acknowledgement from the sender to the receiver, letting it know, I have received your synchronization request, I'm sending you back my acknowledgement. And together, this is how we sort of establish a connection, right? Because let's pretend we just do that first step. So we send from the sender to the receiver, we send a synchronization request. And the receiver just sends back its own synchronization request. Well, because the internet is best effort, occasionally things arrive out of order. So we won't get this bit first, right? So we'll send our synchronization request, and we won't receive back synchronization from the receiver, so we might send over another one. And this acknowledgement prevents that duplication of synchronizations from screwing things up, right? Because every time we send a synchronization request, we're attempting to establish a new connection. And if we already have a connection that's about to be established, well, we don't really need to establish a second one, right? So that second step there, where we send a synchronization and an acknowledgement together, that's crucially important to prevent duplicates. And then back here, it's just to sort of, it's a good logic check to make sure, okay, I've received your synchronization, and I'm glad that I've gotten the acknowledgement from you, so I'm going to send my own acknowledgement back. Yeah, does this sort of make sense to anyone? Does anybody have any questions? No? Okay. So, back up here, I also talked about utilizing a sliding window protocol to help with flow control for TCP. So this is the flow control slide. So TCP uses a sliding window mechanism, which allows the sender and the receiver to communicate about what size packets they're going to be sending. Because the sender might be able to send a packet that's a gigabyte big. Actually, that's huge. A megabyte big, right? And the receiver might only be able to handle a couple of kilobytes, right? Like, not a couple of kilobytes, but like, 1,000, 2,000 kilobytes. And what we'll get into is a situation with the sender receiving packets that are too big for the receiver to process and understand, which is a huge issue, because we're going to have the rest of that information that the receiver can't process be thrown away, right? But it won't be processed. So by using the sliding window approach, we agree upon the correct size that a packet should be before we start sending stuff. And then when we begin to send information, the sender and the receiver should be able to handle that. So sort of reading this slide is a little bit difficult to understand. So we have a diagram, which makes it a lot easier. So we have our sender here at the very beginning. And the application layer of the sender is a write of 2,000 bytes. Okay? And we want to send that from the sender to the receiver. So we send a message with the sequence number of 0, just saying, hey, I'm beginning to establish a connection, right? So in this step right here, we would do a SYN-ACK request, but we don't need to represent that again. So let's just pretend we do the SYN-ACK. And we're going to send our payload of 2,000 bytes. So at the very beginning as well, the receiver has a buffer, or a little part of memory, or something like that. That's about 4,000 bytes big. So sending 2,000 bytes, that's about half the size of the buffer. So we're going to send that across. It's going to hit the receiver. And because it's small enough that it can fit within the receiver's buffer, we're going to put those 2,000 bytes within the receiver's buffer. And it's going to send back an acknowledgement that it read in, okay, so it's 2K bytes, which would be 2,048 bytes, because powers of 2 and all that. So we're going to acknowledge that we did read in all of those bytes, and we're going to establish the window of 2,048 bytes. And what that's saying is, I was able to process the information you sent me, and I'm going to set the size that you can send me in future equal to that size, because I was able to process it, right? So we get that information back to the sender. The sender goes, great, now I can do another write of 2,000 bytes. So it writes those 2,000 bytes and sends them to the receiver. Well, 2,000 plus 2,000, right, we end up with a full buffer. So we're going to send back an acknowledgement that we have now read in those 4,096 bytes, right? And we're going to set the window to 0 because our buffer is full. We can't process any more bytes. If you send us anything else, it's going to get thrown away. So I'm just going to tell you, hey, I'm full, can't handle anything else. Don't send me anything. And at this point, our sender is blocked. Because we sent a bit of information, we need to wait for a response before we can send something new. We get a response right here, but the response tells us don't send anything. So we're just going to continue waiting until we get a response that says, send something. So looking at the receiver, as sort of time goes on, we have a full buffer to begin with. The receiver's application layer does a read, so it pulls 2K bytes out of the buffer. And at this point, we can send another acknowledgement request saying, yes, I have received 4,096 bytes from you. I am now ready to receive another 2K bytes. And at that period, it gets sent back to the sender, and the sender says, fantastic, I can continue sending another 2K bytes. But instead of sending 2K, the application layer of the sender goes, I only need to send 1K, so I'm just going to send 1K across. And that's the state of our buffer at the very end. So just because the size of the window is 2K doesn't mean we have to send 2K bytes every single time. It's just the maximum size that we can send, that the receiver can then handle. And this is how we sort of agree upon in a connection the size and information that can be exchanged between a sender and a receiver. Okay? And then, just because I know people like to go back and read slides later, I went ahead and I wrote down each step here, but just in case this doesn't make any sense. So let's go over sort of the positives and the negatives of each of these protocols. We have UDP and TCP. So UDP is a connectionless protocol, which means there's no guarantee that packets will be received. There's no guarantee that packets are received in order. There's no guarantee that packets may have been dropped. We don't have these sequence numbers that allow us to know, yes, the last bit of information I received is the last information that was sent. And that's sort of the advantage of a sequence number, right? In UDP, you can do a unicast message, you can do a multicast message, you can do a broadcast if you'd like to. So it's very versatile in that way. And because we're not establishing a connection, UDP is a lot faster, right? We don't have this connection overhead of trying to do the SYN-ACK and sliding window or any of that. It's just, here's the port, send it to that. And that's why we call it a fire and forget model, because we're firing off from our source, and we're just hoping it's received. There's no guarantee we'll get a message back. And then TCP, it's a connection-oriented protocol. It's mainly used for unicast communication, so communication between two nodes. We do have data delivery guarantees. So we have guarantees packets will arrive in order because we're using the sequence number to establish what was the last piece of information that was sent. So if I get something new, and it does not follow the sequence order that I'm expecting to receive based on the last thing I received, I'm going to go ahead and ask for a retransmit, right? It prevents duplicate packets from being sent, because if I receive 2 packets with the same sequence number, I'm just going to ignore the second one. And then it helps with drop packets, which sort of goes back to the in-order thing, right? If I get a sequence number that I'm not expecting, I can ask for a retransmit, and that will help me fix the stream that I should be receiving. TCP is slower because we need to establish a connection before we can communicate. But it does allow you to deal with congestion, which becomes a serious problem. So we talked about congestion before, right? We have too many packets being received by a destination, and that destination can't process them. So because they can't process them, it gets discarded into ether, and we don't necessarily want that. So, one second. So if we do have congestion on the transport layer, we need to have ways to deal with that. And sort of the most popular way of dealing with that is called TCP slow start / threshold. So it's sort of a combination of the two. But to begin with, we need to understand what slow start is. So TCP slow start, it's a packet congestion algorithm that sets a defined window size to begin with. So usually we'll start with one, so it's the transport data unit, right? So either one TCP unit or one UDP unit. Really TCP, right? So we're going to send one packet over to our host 2, and that host 2 is going to send an acknowledgement of receiving that packet back. So now one packet has been successfully received. And we don't know the window size we need to establish next. So we're going to try and play around and see what that is, right? So we're going to send 2 packets now. We're going to double the size of the window that we sent originally. And then we get an acknowledgement back that 2 packets have been received correctly. So now 1 packet works, right, and 2 packets work. We're going to double our window size again, and we're going to send 4 packets, right? And host 2 only receives 3 because of some congestion problem that's occurred within our network. So 1 packet's been lost, and it's going to send an acknowledgement for 3 packets back. But host 1 knows that it sent 4 packets in that last step, and it only received 3 acknowledgements. So at some point, congestion must have occurred. Host 1's smart enough to figure that out. So what we're going to do in this last step here is if there's been a packet that's lost, so congestion has occurred, the window's going to revert back to step 1. So we go all the way back to the very beginning, and we're only going to send 1 packet. Now, as you can imagine, this protocol by itself sucks, like really bad. Because effectively what you're doing, right, is you're bouncing a window between being very small and growing until it gets too big and then back to being very small. You do it again and again and again and again. You're going to get what looks like sort of peaks like this in the transmission of your packets, right? So if you're, for instance, what's a good example? If any of you play video games and you have Steam and you're watching packets being downloaded on your Steam account, you don't want your packets to look like that, right? You want it to kind of ramp up to some level and then stay consistent, so maximize the utilization of your network, and then once it's downloaded the game, kind of ramp back down. And TCP slow start by itself does not allow you to do that. But in combination with threshold, we can get there. So what is threshold? So threshold, we establish some sort of shared threshold for how many packets we think our communication can sustain between the sender and the receiver. So let's just say arbitrarily we have 32,000 packets that are being sent. And what we're going to do is we're going to ramp up using sort of the same thing as TCP slow start. We're going to ramp up until we hit 32,000 packets. So your graph will do that sort of exponential increase like before, except once we hit that agreed upon threshold, we're going to stop jumping so fast and we're going to ramp up linearly. So it will kind of ramp up exponentially and then start growing linearly until eventually we'll experience congestion and a packet will be lost. That's just what will happen. And instead of going all the way back down to 0 and restarting again, what we're going to do is cut the threshold by half and we're going to restart from there. We're going to start back at the beginning, ramp up to the new thresholds, and then linearly increase from there. And what that ends up looking like is this. So we have some agreed upon 32,000 or 32K packets, like right here, right? And we're going to do our TCP slow start algorithm at the beginning. We're going to exponentially ramp up the packets until we hit the agreed upon thresholds. And at this point, we're going to linearly increase the size of the window that we're sending. So the amount of packets we can ship through, until eventually we'll hit a timeout, so some sort of congestion issue has occurred. And at that point, we're going to drop all the way down to 0, following the same protocol, right? Following the whole concept of start from window size of 1. But now, instead of our threshold being established at 32,000, we're going to establish our threshold down at 16,000. And what that allows us to do is the majority of the time that we live in our connection will have sort of a maximized amount of packets being sent, right? So the window size will be the biggest it can be and still accommodate both the source and the destination without dropping extra packets. Because if you see, it's sort of like fail early, fail often, right? So we're failing for relatively early on our x-axis, sort of the number of transactions we've occurred. But the next time we'll experience a failure, right, like up here, it's going to be even further out on our x-axis. So we'll have more time transmitting at a higher rate than we would otherwise. Because what happens if we're constantly timing out is we'll constantly sort of be jumping up and then jumping back down like this. So we actually end up spending, it's sort of counterintuitive, right? But you actually end up spending more time at a appropriate level of throughput. So actually, oh, yeah, question?
So eventually we could just provision on the world, not quite long.
Yeah, basically, yeah. Yes, so what you'll end up having, right, because each time you're going to be timing out usually at about the same time. Maybe it'll be a little bit less, maybe it'll be a little bit more, but if your timeout starts decreasing, which, I mean, there could be reasons why that would happen, I guess, then yeah, your threshold would be so far down on the graph that it would effectively be linear, because we hit the threshold very quickly and then it would just continue linearly. Now, the downside of using, so this gets into like additive increase, multiplicative decrease, additive increase, subtractive decrease, all this stuff, where basically very clever people, far cleverer than I am, spent a lot of time way back when analyzing all these different methods of how do we ramp up the packet size and whether or not it will converge on an optimal solution, or at least maximize how long we exist within that optimal solution. And they found that the sort of process of doing exponential ramp up followed by a linear increase outperforms, on average, all other methods. So because you might just wonder, right, why don't we just immediately start from linear? Why don't we just immediately start from linear increase? And it's just that over time, right, over how long it takes us to finish in transmission, we're going to end up spending more time following a method like this at a higher level of window, so a bigger window size, than we would if we just linearly increased the entire time. Does that make sense? Cool. Yeah. And I think that might be it for today's lecture. Yes, I do have a point to make about last lecture though. So I got an excellent question from Aurora, can't remember your last name, sorry, that asked me, what exactly is this table for when it comes to distance vector routing, this one on the right. And there's sort of a saying where I come from, it's like you're like a deer in headlights. It means to sort of panic. So I sort of panicked, I wasn't able to answer the question at time. But effectively what this is when we have that routing table for distance vector algorithm, and we have the expected time to get from a node J to any other node in the graph, and then we have the next node on the hop, that's what this table is for node J. So for instance, if we wanted to calculate from node J, right, this is from node J, to get to node B, we sample each of our neighbors, right, following the algorithm. We sample each of our neighbors, and we ask them, what are your expected travel times to get to B? So A is 12, I is 36, H is 31, and K is 28. And then we look at how long it takes to get from node J to those nodes, so 8, 10, 12, and 6. We add together those two values for each, and then we compare them against each other. And what ends up happening for this particular line, right, is A wins. So A, the hop from J to A, and then from A along some other route in order to get to node B is the shortest. So we update the local routing table for node J to have a weight of 20 and A as the next outgoing line. So that's what this guy represented from last lecture. Does that make sense? And as we said before, this stuff's fairly important when it comes to the rest of the course. So I would focus on distance vector and Dijkstra's. That's definitely good. But does anybody else have any questions about today's material when it comes to UDP, TCP, congestion control, transport layer? No? Pedro, do you want to say anything? Or not really? Okay. Right, well, that's it for today, guys. If you have any questions, feel free to come up and ask me or send me an email. Otherwise, thank you for your attention.
Again, there's only the application layer left, and then
You're done.
yeah. Did you have a look at password 2 by any chance? Any questions about
So what's happening is, so this is from J.
No, because my questions are always not related to the subject, but I link it.
So what we do is set the algorithm.
I'm
Is we query our neighbors, we query them for the routing. So we look at what the value is, so 18,
Like I play a lot, like I play with my friends about it.
and we add this number here to the delay to get from J to that number, which is down here. It's 8, 10, 6.
I don't know what packet it is. And now I like every time they play it, I see it says packet lost. So I understand that there's some maybe
So no,
congestion
we add 8
or some problem in the layer. That's why you see
so 8 to 18
So my question is going to be
is
it
36. 20.
how does that packet loss, or do you need to do so? What,
26, right?
well,
Yeah.
how do they fix that? Because
And then
a
we
lot of
add
my
10
friends
to
don't have
31,
packet
that's 31. We add 6
what's
to
the
36, that's 31, which is 37. We add 12 to 6, which is 18. 18 is the smallest of all those numbers, so that's why we update the routing tables at 18 from.
but they're all the game is
Because it's
just
smallest. Does that make sense?
So yeah, this tree right here, this all gets set as once then but all made.
Yeah.
So it's usually like as this tree right now, and then
As soon as we receive that last act, now we start sending acts.
okay.
So that's when we begin to utilize those.
And is this information still sent as packets, so it's sent in the packets?
Yeah. So it's sent as a it's called a SYN packet. So there's specific packets that do specific knowledge and ecology. And they're a lot more lightweight than a normal packet. It's just like effectively all you're doing is firing off. All you're doing is firing off a signal. Already small. But this is crucial in order to establish a connection. So when we talk about connection versus connectedness, it's basically did we do through the connection first or not. Now, there are iterations on this. And this is where there are different kinds of TCP protocols. Basically, it all comes down to I implement this and so it goes away. But this is the sort of general simple one. That you can do.
Okay, and then on the that's your whole payload, right? So like the first bit is
Establishing. So right before.
So maybe having,
So just before.
it can either be a router in your own home
We'll
network
do our
or
Synapse.
somewhere
Or
local.
same Synapse.
Home
As
network,
soon as we
you
finish
might
our last
use it.
technology, this is where we send the first message.
yeah.
And then we're just going to finish. Like until, let's pretend this is the last packet that's being sent, let's finish it. Like,
And in reality, you can like probably say like
Yeah, exactly. So it can be the physical medium that doesn't support the
is
time.
that like roughly what the packet size
It can be the router.
or is the window like a much higher, like infrastructure is much higher? Like in reality, I wondered like does that represent reality?
Those are the ones that come to mind.
how big it is? No.
Yeah.
So this represented reality back in 2006. Yeah, 10 to change. It's way bigger than something else.
Go to center and then go to the list, and it gives
I
you
find
like the
it's
direction.
easier
I want to know
small powers of two. Yeah,
That's what I'm concerned about. Like,
So in reality, I'm talking about megahertz.
Yeah, so I think it can be to the physical medium. So if you
400, I don't know what that is. I'm not bad at the more conversions.
but if the API is not strong enough, then it's just drop it. Yeah, not strong enough.
So nowadays, whenever you have a megabit connection, we're talking about this, but within the realm of megabytes. A gigabit connection, same thing with the realm of
So I don't know if packet also
For like
that
streaming,
adjustment that they're doing at the server side or if it reflects at the client side. So I'm not sure.
So
Looking into it a bit more.
yeah.
So that one depends. That one depends. Yeah. Because that we're establishing sometimes we're establishing the connection.
Everything that happens.
Yeah, so if they don't play, I mean, it has no
Client.
way of
For me, to me,
detecting.
that's client service. At this university, we're talking about
Yeah, I know
client
the
service.
network.
We establish a connection which allows us to control to throttle to windowing.
Yeah, the bottom three are the
But
ones
when
that
it comes to
affect the
like
network.
Twitch would definitely
Yeah,
use something similar to
that's the one that
they might be using
controls the network protocol, but for the top four affects the transmission and the transportation. So these
we don't want to establish
they're
a
not
connection it's a waste of time.
Exactly. So
But-
the
Yeah,
The
so
bottom
in
three
modern
layers
day we don't
typically
use UDP
implement
as much.
hardware.
It is still a useful
So
technology.
as they usually don't interact,
There's this thing called connectionless
you only
TCP, which might
start
be
interacting with the network with the player and
it's because you're basically just doing UDP.
you create a
And
socket.
that came around because
You're interacting with the from
people began to use UDP to try and fish on servers. So you connect to
I mean, when I
send out
first
those
started,
packets,
I
and
was
it comes
confused
back.
because when
And
I
that
first
can be dangerous. So nowadays, a lot of people just reject UDP period.
and then
because they don't want to
ISO protocol has
something happen. Yeah.
So I realized this is the standard.
it's a reference.
Yeah.
Basically, it's a TCP packet.
So it's a way to think about
So here we have basically nothing. It's still a TCP packet.
But the hard thing is how to combine it with.
So it's still a TCP packet. The only difference is
That's when
we're not
because if you even understand the structure of it.
So when you write software, you write software transfer.
but otherwise it's still
Yeah, I can imagine how confusing it becomes.
sometimes right. So kind of like UDP is we
Have a good day.
yeah. So even in UDP, which I've accidentally left. Oh yeah. Can I go back?
Did you enjoy yesterday?
Yeah.
You were leaving at the time, I think.
Yeah, so there was an earlier class.
But we still end up having source and destination. Sorry, Dad.
Just a few months. But the
Yeah,
previous
right
class.
here. So if we go back to UDP, so UDP packets will still have a source port and destination port, and then in reality it will also have source and destination IP, but that's a different layer than what we're on right now, so that's why I left that alone.
So UDP can send out just packets at like
broadcast them.
Yeah, you can broadcast to the whole network.
And that's why it's dangerous. So how does the connectionless TCP stop that?
Because so what you can do,
Which is the kind of like safety element, I guess.
safety element, yeah. So you can do things like
Can you broadcast with connectionless TCP or can you just unicast?
that's a good question. I actually don't know. But I mean, you have checksums, you have options. Oh, I forgot to talk about urgent pointer. It doesn't really matter. You have options you can set in order to say I come
What's
from
the
this.
urgent pointer? Is that like a...
So basically, your urgent pointer is a pointer to the part in memory of data where the important part of the data starts. So what you might have, right, is you might have a TCP packet which you're sending for command and control instance to do some sort of CNC. And I don't care about any of this crap in command and control. I just want to be told where inside of this packet do I need to look in the payload to find the thing I want. And this just gives you the address of that. Yeah.
So it basically points at it.
Yeah,
Allows
it points to
to
the
skip.
thing that you...
allows it to skip some when it's reading.
Yeah, instead of having to unwrap the packet,
Yeah.
you can just immediately find a bit of memory that you need to grab. But yeah, I mean, stuff like that. Also, it's about like source control stuff. So one of the issues with UDP is you can sit on a network, and because you don't need to establish a connection, you can spam everything. And do you guys talked about like DDoS or denial of service?
When you try to...
When you overload the server
by just spamming it with stuff. So it's a really easy way that, if I can first off get within a subnet, I can just sit at that subnet and spam everybody with UDP, and now they can't take in anything else because I've clogged up all of the networking traffic. Whereas TCP...
So that's a DDoS, basically? Is that what a DDoS is?
That's a form of DDoS, yes, a form of DDoS. I think there are other ways to do DDoS, but that's one way to do it. Or DOS, yeah, sorry, denial of
DDoS
service.
is distributed, so you're running across multiple clients doing it at the same time.
Yeah, so he's the distributed person. I'm there.
So UDP is faster. How much is faster?
That's a good question.
What is faster?
What is faster? Well, because you don't need to do the three-way
We're
handshake.
talking about...
You didn't quantify it.
I didn't quantify. No, that's true.
Are we talking about milliseconds or
Are you talking about
nanoseconds?
an
Like,
order of magnitude?
Yeah,
or
what
2 orders of
order of
magnitude? Or are you talking about twice as fast?
So what I'm talking about is you don't need to establish.
Yeah, I understand that, but I want to know how much is faster.
I don't know.
How much faster is faster?
I don't have a quantification for that, but for the
You need to have
purposes,
a quantification.
I do.
So the connectionless TCP would still do the three-way handshake, and that's why. Is that what you're saying?
Most of
And
the
that's
time,
why it's safer than UDP.
So it depends on the implementation, right? So that's why I didn't go into connectionless
much,
TCP.
okay, yeah.
There are versions. I mean, most of the versions I know of just skip the three-way handshake, right? So it's effectively a UDP packet,
Right,
but you
okay.
can still do source control. So you can still the whole sliding window issue where we're modifying how many. We're basically saying I can take in this much, I can't take in this much. You're still doing that, and that is what prevents things like DOS.
Because the buffer...
Because I can send something back saying stop sending me stuff. I can't take
cannot
anymore.
accept it,
Yeah,
Yeah.
I'm finished. Yeah.
Nice. Thank you very much. That was really helpful.
No problem. Yes, even though I got some difficult questions.
Have a nice
He's
Christmas
very
break.
talented.
Are you flying or
Yes, yeah,
traveling?
we're flying. When are we flying out?
Sunday.
Sunday. We're flying out Sunday.
Enjoy the holiday period.
Thank you.
Thanks for that.
Yes.
Cheers.
Cheers. All right, no problem, guys. Oh God.
Job.
Thank you.
Well done.
Who?
Thanks again for your help.
Yeah, of course. I had a blast.
Enjoy the experience.
Seem to.
I did. I did. You know, I did a lot. I felt.
I think you did a good job of presenting yourself and not humming and hawing. And some people are terrible. They're like, and then they get into the, like you say, the deer in headlights all the time. Yeah, I think you're very consistent about how you got it over and you did from slide to slide. Excellent.
Oh, yeah,
Thank you.
Yeah, probably one of the best speakers in the
I wouldn't
PhD
say that.
class. No, but
Say that. Well, to be fair,
that's a big class.
back when we did the masters together, whenever we needed to do a speech, and they'd ask us, "Who do you guys want to do the speech?" Everybody would be like, "Oh, Ian, right? Ian will do the speech." And I was like, "Yeah, I'll do it. I'll take it."
I think that's a reflection of maybe the education system in the US. Maybe they practice those
Oh, yeah.
skill sets a bit more than they do here in Portugal. Because, yeah, they're not really good.
I did
I
two.
never did any. I mean, I did the PhD. I did masters and PhDs with it. And I didn't do any of it. And then I get to America and I'm supposed to present stuff on stage. And I gave the first presentation, and they're like, and then they sent me off to a class to learn how to speak.
Yeah.
It was so bad, because I'd never been through any of it.
Because in high school you do theater and all that
Yeah.
stuff, I imagine that carries on and helps you
Some people.
develop.
But it's not mandatory. So I never did theatre, and I made it to university. And for shits and giggles, I took a public speaking course. But that wasn't, to be honest, it was more of an English course. It was more about how to write a speech. And then I made it to my final dissertation. And I was, because I'm very energetic, so I was selected as the person to present my dissertation. And it's this one professor, Dr. Margaret Heil, from my undergraduate school. She was a business person who brought in to help all the computing students. But she drilled us over and over and over and over again on how to do a presentation. And I think you came to that one.
Yeah, I did. You did a really good job there.
I
You're
blacked
way
out.
better than everybody else.
You know, I credit Mrs. Heil, or Dr. Heil. Yeah, American, but it's a very German name. But yeah, no, hopefully it wasn't too bad.
You're going to celebrate now a little bit.
Yeah, we're going to go get some lunch. Yeah, get some lunch and then go back to do some work.
It's been a pleasure.
Thank you, Pedro.
Speaking with you, and,
I'll see you next year.
Yeah.
Yeah. See you in the new year.